every spacecraft must be cooled in space. It's why we chose to use some of the water in our radiation protection layer as a cooling system. Water flow near interior spacecraft cavities absorbs heat and transfers it to a cooling system, which radiates the heat to space. So the water container material must allow the water to absorb the heat, the objective of our experiment. In the experiment, we used 2 glass petri dishes of different weights and 1 plastic petri dish, which are used as containers. We poured 30 milliliters, measured by a digital scale of distilled water, into each dish using a pipette and recorded the system's initial temperature with a thermometer. Then, we heated it up on a heating plate for exactly 30 seconds, followed by temperature measurements of the water. The heating plate was preheated, so it reached a constant temperature, and after each heating cycle, we stirred the water for a few seconds to reach equilibrium and to even out the temperature of the system. The heating process was repeated 3 times for each material. We documented everything using pen and paper, and all results were later calculated in an Excel file. When comparing the results, we noticed how the temperature increase was inversely proportional to the dish's weight, while still affected by the dish's material. After further analysis, we realized that what really determines a material's suitability to store the water is the multiplication of its mass m and its specific heat capacity c, in ratio to the water's m times c. When this ratio decreases, the temperature of water increases, and vice versa. Since the C of glass and plastic are similar and drastically lower than the waters, we concluded that the mass of the material is more important than the type of material itself. Our full experiment report provides a detailed explanation of the methodology, results, and analysis presented here.